about the homework. Right. So I have these really, really awful matrices. And I hope this works out well for you. I tested them twice. So. For the following matrix, for the matrix, I want you to find the rational canonical form, primary rational canonical form, and Jordan canonical form, if possible, for this matrix over field Q. And similar in number 2, I've got another just awful matrix, and I want you to find all the canonical forms, rational, primary, rational, and Jordan if possible, over the reals, and then find the canonical forms of this matrix over the complex numbers as well. And I think in this one it should make a difference. And number 3, I want you all to be Sherlock Holmes. Right? We have a history of Watson. I have this matrix. And what do I know about this matrix? Well, it represents some phi with respect to some basis for V over F. It's got a maximal set of 3 linearly independent eigenvectors. That's one clue. The characteristic polynomial, that is the polynomial you get hidden eigenvalues, has degree 9. The minimal polynomial has degree 5. 2 of the phi invariant subspaces are of the same dimension. And finally, all of the canonical forms, including the Jordan form for this matrix, are all the same. Find what the Jordan form is. And finally, here's another application of decomposition of linear transformation. And this problem would make my colleague probably very happy in a certain sense. Consider the group GL3C2, which by this notation, what I mean is 3x3 matrices over Z2 that are inverted, right? So this is a group under multiplication, right? Anybody know how many elements it's got? I think it's got 168. See if you can. 168. Find the number of conjugacy classes in this. Remember when you all did the class equation and all this, and you looked at conjugacy classes. Find the number of conjugacy classes in G and a representative from each class, and you will find that this matrix representation is canonical form to make this problem. You've got 168 elements to plow through. It makes this much easier. Okay, this one should be a fun thing, despite what you heard from people last year. Any questions? All right. Okay, so last time we were talking about K of X. So we had this finite dimensional vector space E. We have a linear transformation from E to E, and we considered E as a KX module. And we made some observations about these phi cyclic subspaces and how you can break up. The last theorem that we had, we talked about if you have a linear transformation, then this linear transformation is phi cyclic with minimal polynomial. X or plus A or minus 1. So this transformation is phi cyclic and has that minimal polynomial if and only if the dimension of E is R and there's a basis of E relative to which the matrix looks like this. This is called a companion matrix. Now, let me give you my apologies, and this is just my weird traditions. You have to, all the canonical forms I'm going to do, you're going to have to do the transpose if you like to multiply your vectors on this side in a column fashion. These are set up for rows on this side. It really doesn't make that much difference. And I'm a mixing matcher because I tend to like multiply columns like that. But I like canonical forms this way. But I want to demonstrate if we let V what happens when I apply V, this matrix to V? Well, first row, first column, I get 0. So here's what V does to it. First row, first column, get 0, then I get 1, and then I get zeros forever. Right? So here's V, here's phi of V. Agreed? That's my next basis element. I'm doing the phi cyclic thing. Now let's take phi of V and apply it again. And what happens now? Well, now when I apply this, I get 0, 0, and then 1 in the third. So y'all see the pattern, how it's kicking the one down the road? So this is now phi squared of V. And now when you apply this, it just keeps kicking the one off down. Now, of course, the thing you might ask is what happens to this last one? What happens to this last one? Well, this gives you minus A0, minus A1, minus A2, minus AR minus 1, right? And notice, this makes sense, because notice that phi of V, well, phi R to V is equal to minus A0 V minus A1 phi of V minus AR minus 1 phi R minus 1. And so really what this should give you is phi of the RV, and it gives you this strange linear combination of the previous ones, but that's exactly from this polynomial relation right here. Everybody okay with that? That's exactly. So this is why this works. This is why it's phi cyclic. It takes this vector, kicks it to the next, kicks it to the next, and finally it kicks this vector to this linear combination of the previous ones, which gives you phi to the R power. Right? This is called the companion matrix. And I'm going to use this companion matrix, this form, to get most of the canonical forms. But first, let me give you this corollary. And once I get this corollary, I'll show you how to tackle it. Let phi from E to E be a linear transformation of V over of E over K, then V is well, I guess let's say E is phi cyclic. And has minimal polynomial x minus lambda to the R power, I guess. If and only if m E is equal to R, and there exists a basis such that E as matrix lambda 1 0 0 0 lambda 1 0 0 0 lambda 1 0 0, 0, 0, 0, lambda 1, 0, 0, 0, 0. Oh, lambda. How many of you have seen this form, right? This is what we call an element Jordan block. So the blocks are going to look like this for the rational canonical forms, and they're going to look like that Jordan form. By the way, does anybody see at this juncture a hazard for the Jordan form? This seems to be pretty restricted, right? I'm not going to be able to always factor a polynomial. Right here, I'm fast to lose easy peasy. Polynomial, I don't care. This requires me to factor a polynomial into a product of, or into a product of powers of irreducible linear polynomials. So to be able to use the Jordan form in general, I have to be over an algebraic equation. Right? You can use the Jordan form sometimes if you get lucky enough to have a polynomial that splits down into products of powers of linears, right? If your polynomial is x minus 1 times x minus 2, you're good to go. Or x minus 1 cubed times x minus 5, you're good. But if your matrix has a polynomial, let's say over q, something like x squared plus 1, you can't factor that into linears over rational numbers. Okay, so let me briefly outline why the corollary follows from what we had before. For b minus the identity. Notice that q x minus lambda to the r is minimal polynomial for phi if and only if x to the r is minimal polynomial for pitchfork. Now, apply previous theorem in case that minimal polynomial is x to the r. So the previous theory, if the minimal polynomial is x to the r, then what does this block look like? Well, this block is going to have ones on the super diagonal, and everywhere else is going to be a 0, because if the minimal polynomial is x to the r, then all the a's here are 0. So that bottom row is 0. So the matrix looks like this: 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, and 0, 0, 0. Oh, oops, here. I'm mistaken my notes because that's it. That's plan there. Okay. Now add back lambda I. We get this credit. Add back the lambda I to get the phi. Okay. Any questions? Okay. Well, let's get to the fun part. Let's start figuring some of these out. Now, the first example, this is one of those ones where I gotta say, wait for it, because I know what the first protest is going to be. I would protest. Example. Let's suppose, just for giggles, that we have a linear transformation with invariant factors. Transformation over Q with invariant factors. Let's say, let's call it, well, call this something. Q1 x squared plus 1 squared x minus 2 squared. And I've gone ahead and multiplied this out. This is x6 minus 4x5 plus 6x4 minus 8x cubed. Plus 9x squared minus 4. And Q2, I've got another invariant factor. X squared plus 1. And x minus 2, which should be x cubed minus 2x squared plus x minus 2. And Q3, x squared plus 1. Right. Notice that my smallest invariant factor divides the one above it. The one above it divides the top one. Right? Everybody agree with that? Okay, let me ask you a couple of questions. First of all, what's the size of this matrix? How big is it? Well, these are the invariant factors, right? I'll give you a hint. Product of the invariant factors should be the characteristic polynomial. So how big is it? It's 11 by 11. Now, I bring that up now because please don't expect me to write 121 entries for this, right? I'm going to shortcut this a little bit, right? So this should be 11 by 11. The characteristic polynomial should be x squared plus 1 to the 2, 3, 4, and x minus 2 to the 3. Should be the product of the invariant factors. Am I okay with that? What's the minimal polynomial? This is just asking, like, what's the exponent of the group, right? If I have Z2 cross Z6, you know what the exponent of the group is? The exponent of the group is the smallest n such that n times everything in the group is 0. The minimal polynomial matrix should always be the largest invariant factor. Okay, lots of canonical forms. So let's do the straight up rational canonical form. The rational canonical form uses the invariant factor of the all. So what this tells me is in my rational canonical form, I will have three blocks, one for each invariant factor. They all look like this, according to whatever the appropriate polynomial is. So I'll do the biggest one first. What order? Doesn't matter. You can permute the blocks however you want. But I've got a 6 block that should look like this. 6. And then finally, -4, 4, -9, 8, -6. Basically reversing the sign of these coefficients. Everybody see how I got that first block? 6 by 6 because of the degree of this, and you just build this with the polynomial that is makes it P6. Everybody okay with that? The next block should be a more modest 3 block. So go diagonal down here. And I should run this backwards. 2 minus 1, 2. That corresponds to Q2. And the final block should be a 2 block corresponding to that. And I guess that's my. All the other entries that I've left out are all zeros. Everybody okay with that? Everybody see how to build these blocks? Now, there's something else called the primary rational. And it's the difference between invariant factor decomposition of a module and the elementary divisor. So now what we need is the elementary divisors to run the second. So in my second installment, let's look for the elementary divisors. What are the elementary divisors here? Just cherry pick off the prime powers. Okay, let's be careful over Q. Would everybody agree that x squared plus 1 is prime over Q because it's an irreducible polynomial? So the elementary divisor should be x squared plus 1 squared x squared plus 1 and x squared plus 1. Notice the x squared plus 1 appears twice. And the rest of them should be x minus 2 squared, which is x squared minus 4x plus 4, and then x minus 2. 1, 2, 3, 5, 6, 7, 11. Adds up to 11, so that's good. Everybody see how I picked up the elementary divisors? Now you just do the same stuff you did before, right? Only now my blocks, there's gonna be more blocks and of more modest size. So for the primary fractional, primary corresponding to fact of doing elementary divisors, well, let's just go down the blocks. This one's a 4 block. 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And then I guess -1, 0, -2, 0. Then I'm going to have the block for x squared plus 1. Another one just like it. And now I've got to go through this rigmarole and get a 2 block for this. 0, 1, -4, 4. And then finally, I get a 1 block, which should be actually 2. There's no 0 1s because that's degree 1. You just have the reverse sign of it. Constant. Everybody see how we got that? I should have 11 up the diagonal, 3, 6, 9, 11. What about the Jordan canonical form? You are right not to answer because you can't do the Jordan canonical form. What's the problem? This thing is not linear, right? This irreducible over Q, it's not linear. Does everybody got what they need right here? Because of the x squared plus 1 business. It's irreducible. So, no Jordan canonical. This matrix over Q. So change to C. Well, now we're going to have to revisit our elementary divisors. Notice that now x squared plus 1 is equal to x plus I times x minus I, right, over C, right? So our elementary divisors are actually what's x plus I squared, x plus I, x plus I. Which I guess I better multiply this out. This is x squared plus 2ix minus 1. And then I have the same bit with the factor of x minus I. So I have x minus I squared, which is x squared minus 2ix minus 1. X minus I, x minus I. And then these ones are, they're the same as they were. 4 x minus 2 squared, x squared minus 4x plus 4, and then x minus 1, 2, 3, 6, 7, 8, 9. Good. Those are now my elementary divisors if I'm over complex. So my Jordan form over complex numbers. Well, let's go through it. We've got a two block here. So we've got 0, whoops. Here, my lambda is, minus I, isn't it? So I'm gonna go two block, minus I 1, 0 minus I. So that's a two block for that. Then I'm gonna get minus I. So these are two little wimpy one blocks. So it's just minus this. Then I'm gonna get another two block with plus I. So it's here. And then I'm gonna get an I. And then I get a two block from this. Eigenvalue is 2. And then and again, whenever I leave stuff out, these matrices, the rest of it is are zeros. Okay, any questions like that? Any questions? So that do y'all see how to implement this? Right? I mean, you just take your invariant factors or your elementary divisors and you build blocks for each one of them, right? Okay, who's gonna complain? Come on, there's gotta be a complaint here. I know. Well, look at this example I gave, right? Poof, I'm like freaking Gandalf here, pulling invariant factors out of all sorts of places, right? How do I even know if I walk up to you on the street and give you a matrix? How do you know what the invariant factors are? Right? That's the problem, right? Because once I get here, once I say, "Oh, look, invariant factors," it's not too bad, is it? Right? You just kind of throw things together in the matrix and do what you need. The question is, if I give you some matrix, like those horrible things that you do in homework, how do you know what the invariant factors are in the first place? That's the real problem. So I'm going to give you this theorem without proof, but the proof is not super hard, but it's only take 2 days to do it. Theorem, let A, and I will do a demonstration of this. Let A be an n by n matrix of the field. Then the matrix of polynomials x I n minus A. Well, actually, but it doesn't matter. And by the way, this would be the setup you would do if you wanted to figure out what the eigenvalues are, right? Subtract x along the diagonal and take some determinant. But that's what we're going to do. We're not going to take the determinant here. This is equivalent via elementary row operations from the ring K of x. And when I say row equivalent, I'm going to tell you what the playground is. Via elementary row operations. And actually row column operations over the ring Kx. So you can invert elements of K because they're in the ring, but you can't invert X. You can't do that. To a diagonal matrix. So you can always turn this into a diagonal matrix with diagonal entries. F1 divided by F2, or dividing F2 all the way up to dividing Fn. And the non-constant ones are the invariant factors. So, you can always reduce that matrix A minus X I N and come up with a diagonal matrix where the successive diagonal entries divide each other in succession. And the ones that are not constant will be your invariant factor. So let me do a couple of examples here. And this, see 5, 1 minus 12. Okay, so let's look at this matrix here. What are the invariant factors of this? So look at 5 minus X, 1 minus 2 minus X. Okay, and I'm going to go bananas with the row and column operations. The first thing I want to do is I want to use this 1 to start wreaking havoc. So I'm going to take this out. So how do I take this out? I multiply the top row by X plus 2 and add it to this, right? And that'll take this to 0. X plus 2 is an element of the ring. So X plus 2 comes the first row and add it to the bottom row. Now it's going to get 0. When I multiply this here, I'm going to get a minus X squared. I'm going to get 2X and 5X is 7X. And then that's going to be minus 10. Oh, it's supposed to be X plus 2. X plus 2, right? That's going to be minus X squared again. That's going to be 5X minus 2X is 3X. And this is going to be 10 minus 12 is negative 2. Right? And now I can multiply this column by X minus 5 and add it to this. So essentially, right, because that's a 0 down here. And so if I change the columns, I get this. And I can change the sign of that lone X squared. So turn that to 0, flip the columns, change the sign of the bottom one, and I get this. This has got a single invariant factor. It's X minus 2 times X minus 1. So that tells you how to get primary, rational canonical form. Notice that the largest invariant factor is the minimal polynomial, which is this thing. Right. So in this case, the minimal polynomial and the characteristic polynomial coincide. Let's do another 1 or 2 of these. All right, how about this one? Let's look at matrix. -1, 0, -1, -2, 1, -1, 2, 0, 2. By the way, if you want to be super clever, can anybody make an observation about what I expect to get in the outcome of this? This matrix is single, isn't it? So I expect one of my invariant factors at least to have a factor of X in it, right? Because 0 has to be like that. I expect that to turn out. So we'll see what happens. The first thing I'm going to do is -1 minus X, 0 minus 1, -2, 1 minus X, -1, 2, 0, 2 minus of x. And you know what? I'm gonna put this on top. And I'm gonna use this to kind of kill stuff. So I'm gonna add this to this and leave that the middle row. That's gonna be 0, 1 minus x. And it's a straight up add. So it's gonna be 1 minus x. And actually, get the bottom row, I'm gonna multiply this by, I guess, x plus 1 times a half. And then that'll kill that. Everybody agree with that? So if I multiply this by 1/2 times x plus 1, that'll kill that. So that'll make that a 0. Multiply this, and this is a 0. And we'll see, what do I get here? This the product here, 1/2 x plus 1 times 2 minus x. I've got to multiply this and then add it to this. This is 1/2 of minus x squared plus x plus 2. So this becomes minus 1/2 x squared plus 7 minus x. Minus 1/2 x squared x, and then plus 1. So when I add this to this, the ones cancel. I get minus 1/2 x squared minus x. Oh, and everybody with me? Now what? Anybody see a good move I can make? Remember, you want to maximize zeros here. Right? Sure. So one of the things that I guess I could do is I could take this and add it to this, right? Take the middle column, I figured one, and add this, make this go away. So this makes the matrix 2, 0, 2 minus x, 0, 1 minus x, 0, 0, 0, and I'm going to go x squared minus x. I don't like that 1/2 there. And what did I do? I mean, that's another one of my row operations. I multiply that bottom row by negative 2. Now what? I guess I can make that a 1. Now I can multiply this column by x minus 2 and add it to this. Kill this. And I get 1, 0, 0, 0, 1 minus x, 0, 0, 0. Let me point out this is x times x minus 1. So what do I did in this case? My invariant factors are 1 minus x and x times x minus 1. Notice the stuff that what's my characteristic polynomial should be x times x minus 1 squared. All right, that's a characteristic. The minimal polynomial is this. Notice I've got a factor of 0 x here, so that means that I've got an eigenvalue of 0. Which is good. Right, okay, any questions on the manipulation of this? All right, so let me give you a kick down the road for what you're going to do on my homework. I mean, look, nobody wants to take a 6x6 matrix, subtract X from the diagonal and do this stuff to a 6x6 right off, right? Take the matrix and find the Smith normal form of this matrix. You can do this with almost, you can do this free online, you know, without even having to pay anybody. MATLAB will do it, Maple will do it, any of the software that has it. Here's what I want you to do in the homework. I want you to find the Smith normal form by telling a computer to do it. And I want you to tell me on your homework, a computer did this for me, and here's what I got. Then what I want you to do is take the data, so you get matrices that look like this, and then interpret it. Give me the canonical forms again on it. Now, all these computer algebra systems will also do canonical forms, so you can check yourself. But I want to see that you get the invariant factors and can go from there. Okay, any questions? Questions? Y'all feel comfortable with being able to do these computations? Okay. So, at the end of this, and actually, again, I tell y'all, I hope that this helps you, because I think that if you have not and are planning to take the algebra qualifier, what we've done here, I hope, and the homework also will help you a little bit. It'll help you be better at algebra, but I think it'll probably help you with the linear algebra side as well. So, this chapter is a favorite of almost everybody. Fields and now what? And this is the place where the catalog theory actually has a lot of really cool applications. Maybe if you want to make arguments, math is art, this is one of the real places to do it. So before we get into the cool stuff, you have to go through some basics about what fields are. Field extensions. First, let me so here I'm let R and mean the brain I can follow the rule. Number one, 0 is a maximal ideal. Two, R minus 0 is a group under multiplication. So let me verbally go through this, right? Suppose 0 is maximal ideal. Take X to be non-zero. Look at the ideal generated by X, right? That's strictly bigger than this, but 0 was maximal ideal. So the ideal generated by X has to be the whole ring. Therefore, 1 is in the ideal generated by X, so 1 is a unit. So that means that every non-zero element is a vertical. And on the other hand, if every non-zero element is a vertical, then every proper ideal except for 0 is the whole ring. Any ring satisfying one, hence both of these, is a field, right? So that's kind of an interesting way you probably haven't thought about it. more, but they're precisely computed rings with identity where zero is maximum ideal. And more familiarly, they're the ones where the non-zero elements form group of multiplication. Okay, any questions? Questions? Well, I encourage you all to be at the math club today. Other than that, enjoy the homework. It's fun. And I will see you all on